I would like to talk about a research entitled Inference System for Automatic Identification of Braille Blocks using a Pressure Sensor Array. Background of research. At present, the number of visually impaired people in Japan has exceeded 300,000. It includes the acquired visually impaired who make up 1/3 of all blind persons. A lot of accidents, such as falls on the platform involving visually impaired people, occur. According to the survey of the Ministry of Land, Infrastructure, Transport, and Tourism, Japan, the cause of some accidents in misidentification of Braille blocks due to mental stress while walking in class or wear of Braille blocks. Moreover, the acquired visually impaired people have differences in the ability to identify the Braille blocks. It is known that the acquired visually impaired people cannot walk alone with only a fight cane or a guide dog. Therefore, it is required to develop the equipment for helping them to identify the Braille blocks automatically. There are some systems to assist visually impaired people walking using RFID-tag, using QR code, using ultrasonic wave or camera. Next, I will review some examples. Firstly, a walking assistance system using RF tags. Passive RF tags were installed in the station platform. As visually impaired people holding the fight cane containing reader sensor come up there, their smartphone give attention to them with vibration. The QR navigation system uses the QR code sticker put on the warning Braille blocks. Accurate location information linked to each QR code could help visually impaired people walk. However, it was necessary to find the QR code with a camera. Visually impaired people were forced to keep their walking posture constant to detect the QR code accurately while walking. The object of our research, the following requirements of the assistive system for visually impaired people to walk safely, a necessity of extra infrastructure, low cost, ease to use, identification of warning Braille blocks with high accuracy. We propose an inference system for the automatic identification of Braille blocks using a pressure sensor array. This figure shows the final goal of the proposed working support system for visually impaired people. First, a user attaches the foot pressure sensor array and then works on the Braille blocks. The aggregation data by a microcomputer is sent to the cloud computer to be learned. The running process is executed by Matlab on cloud computing, and run weighted coefficients by neural network can be downloaded to an inference chip. Finally, the user can get the information of Braille blocks from the inference chip by vibration or voice. To realize our system, firstly, it was necessary to develop a sensor array to detect the Braille blocks. There are several kinds of foot pressure sensors that were already in commerce. They are used for sports, such as golf training or running form analysis. However, they are not for Braille block detection. Therefore, we decided to make a foot pressure sensor with low cost and easy to make. This shows the foot pressure sensor array to detect the Braille blocks. Our pressure sensitive sheet was fabricated in the lattice pattern. the pressure sensors could be formed at each intersection area of the conductive copper tape. This figure shows the pressure patterns measured by the pressure sensor array when the user steps on the flat floor, guiding Braille block, and warning block, respectively. Each pattern was depending upon the type of Braille blocks on each the user stepped. Then we learned the difference in these patterns by neural network. Running conditions of neural networks are shown as follows. It has extremely simple neural network structure. This shows the configuration matrix by Matlab. The overall identification performance was 97% or more. The weighting coefficients calculated by Matlab were written to the inference chip. Figure A shows an example of the experimental results of inference performance while stepping on the warning Braille block. We can see that during the step transition periods, there existed some erroneous inferences, marked asterisk in the graph. This was because the chip inferred the user stepped on the guiding block, even though stepping on the warning Braille block. To reduce such errors during the step transition period, we adapted majority decision processing using the result of 5 inferences. Figure B shows that the errors occurring during the transition periods of the step change could be reduced. Table shows the average results of inference performance. The experiments were made under the following conditions. The user stepped the flat floor, guiding block, and warning block 500 times respectively, and the performance was evaluated by counting the number of correct or incorrect inferences. The inference performance did not attain the simulated results by Matlab. This is because in the practical experiments, they were the difference in stepping forms. I would like to demonstrate our system from now on. First, a user will step on the warning block and next step on the guiding block. Finally, step on the flat floor. LED lamps will illuminate depending upon the Braille blocks. Stepping on the warning block. Stepping on the guiding block. Stepping on the flat floor. Conclusions. We developed a foot pressure sensor array with low cost and ease to make. We use Rasphberry-Pi 4 to realize an inference chip with high identification accuracy in real time. We propose majority decision processing to reduce error occurred transition periods. As a result, improve inference performance. Future works. I will repeat experiments for practical use with the cooperation of visually impaired people. Thank you very much for your kind attention. From Shimanami Kaido in Eime Prefecture, Japan.